Welcome to my channel RLD Academy. This is tutorial number 2 on op-amp. Here I'll discuss one interesting problem for competitive exams like GATE. This is the problem. Look at this figure carefully. Here one op-amp is given and the circuit, here this resistance is 1 kilo ohm, and here this is 1 kilo ohm and 3 kilo ohm connected, and one load R, this is 8 kilo ohm, is also connected at the output side, and this signal, input signal is 200 millivolt applied. So we need to find out the voltage V0. We'll try to solve this problem. Now, to solve any problem related to op-amp, we'll use these following 4 concepts. So first one is virtually connected concept, that terminal, inverting terminal B minus and non-inverting terminal potential V plus, they are same if the circuit is having one negative feedback, and one assumption is that the op-amp is having infinite voltage gain. If it is true that infinite voltage gain and circuit is having one negative feedback, we can say that the inverting terminal and non-inverting terminals are virtually connected. This is the first concept. And second concept is that current entering to the op-amp is 0. That means this I0, this I minus and I plus, the current entering to inverting terminal and current entering to non-inverting terminal, they are basically 0 ampere, means no current is entering to the op-amp. This is because of infinite input impedance of the op-amp. So this is the assumption that input impedance of op-amp is infinite, then there is no current entering to the op-amp. So these are 2 concepts. And then the third one, this is inverting amplifier. So this standard one that we can use this gain factor. So you know that there is a feedback, negative feedback here through RF, and if this resistance is R1, this is RF, then you see from this source VI, the current II is supplied by the source, it has to go through RF because there is no current entering to the op-amp. So in that case, we will find the gain, this V0 upon V1 is simply minus RF upon R1. This is a very common one that we have discussed in previous lectures, and it does not depend on the load resistance RL. This is important. So whenever we will get this kind of figure that we are sure that it is a inverting amplifier, we can use that one. Now for this non-inverting amplifier, you see this one. So this is R1 and it is RF, and input voltage is applied here. Okay, and for this one the gain is 1 plus RF upon R1. Okay, so we'll make use of this non-inverting amplifier as well. Okay, whenever we will get this kind of circuit. Okay. Now, I'll consider the circuit here with resistances Ri, with this one, this is your R1, this is R2, this is R3. And we'll try to find out this gain of this amplifier, means V0 upon Vi. We'll try to prove that this gain V naught upon Vi will be equals to this one. This minus sign, this R3 upon Ri times 1 plus R1 upon R2 plus R1 upon Ri. Okay. Now before going to prove this one, I want to see whether this result is giving some meaningful thing or not. Okay. So first, if we consider that R3 equal to 0, so R3 equal to 0 means this is short circuit, this is not there. Then what is circuit? The reduced circuit is like this, because this one, you see this is your R3 is not there, it is 0, then R2 is connected at the output end. So this is the circuit, it looks like a inverting amplifier simply. Okay, so this feedback resistance are 1. So what is the gain? For this one, gain is V naught by Vi equals to minus R1 upon Ri. And you can look at here, if R3 is 0, this part is absent, you will vanish. Then you will get minus times R1 upon Ri. It makes sense, right? Again, if I consider R2 tends to infinity, means, so you see this R2 is infinity means open circuit. Then what is circuit? The reduced circuit is this one. So this R1 plus R3, they are connected in series, that will behave as a feedback resistance. Okay, so and again it is a inverting amplifier. So you see the gain is V naught upon Vi is simply minus R3 plus R1 upon Ri, and that you will get here. If R2 is 0, this part is absent, then this R3 plus R1 upon Ri is the voltage gain. Okay, so from this equation we can easily derive these things with the condition R2 tends to infinity. It is also making sense. Okay, next we will try to prove this one. Okay, now I will give you two methods to solve this problem, to prove that equation. Okay, that gain. First method. Now here I have shown that this part, it looks like a T network. This is one arm, R1, this is R2, this is R3. Now we'll try to convert this T network to pi network. Okay, means start to delta conversion we can go for, right? So that thing we have discussed in the channel, you can go through that one. Now this is your T network. The R1, R2, R3, they are connected with the nodes 1, 2, 3, and we can convert it to this pi network where this resistance is R13 between node 1 and 3. This is suppose R12, this is R23. Okay, and where this R13 we can find as R1 plus R3 plus R1 R3 upon R2. Okay, so between this 1 and 3 resistance is simply this resistance R1 plus R3 plus R1 R3 multiplication upon R2. Okay, similarly you can find out R12 and R23, but these two will not be required to find out in this problem. So you see how we'll use this one. Now, so this is the original problem, and we'll replace this T network by pi network like this. These are R13, R12 and R23 we have connected, and now here you see this end is grounded, thus this is grounded, this is also grounded. Okay, and here R13 is R1 plus R3 plus R1 R3 multiplication upon R2. Now you can check this conversion R13. How can you check this one? Simply if you consider R2 equals to 0, so you see if I make R2 equals to, infinity, not 0, R2 equal to infinity, then it is open circuit. So these two resistance R1 plus R3 will be same as R13, right? So R13 will be R1 plus R3 because R2 equals to infinity, so this part will vanish, so you will get R1 plus R3. It implies that R13 is more than R1 plus R3 when R2 is non-infinity. Okay, it's not infinite, it's a finite value, right? Now consider this figure. Now we can rearrange that figure. So these are 1, 2 I can connect here, and these are 2, 3 I can connect at the output side. Okay, so R2, 3 is behaving as a load, and R1, 2, you see here, this is the virtually connected, virtually grounded. So this is 0 potential, this is 0 potential. No current will flow through R1, 2. So we can ignore this R1, 2 resistance. We can omit this one. We can remove this one. And then after removing this R1, 2, you will see this figure is simply a inverting amplifier. With this resistance Ri, feedback resistance R13 and load resistance R23. Okay, same current is flowing through Ri and R13. So it is a inverting amplifier, and we know the gain. So V0 upon Vi. Now we can simply write minus R13 upon Ri. And R13 already we have got. So that is R1 plus R3 plus R1 R3 upon R2. So if I rearrange this one, so you see this first term, these two terms I have considered first. R3 I have taken common from here. Then it is 1 plus R1 upon R2, this part, and then it is R1. You see, then if you divide Ri, you will find that R3 upon Ri times 1 plus R1 upon R2 plus R1 upon Ri. So it's proved, right? So this is the first method. Next, I'll discuss the second method. Now here, I'll consider that this current is II, and as in the op-amp there is no current can enter because of high input impedance, so this II will flow through this R1. Okay, so you see this concept is similar to inverting amplifier, though this point is not exactly the output side, but somehow it is connected through this R3 element, then it is connected to output side of this op-amp. Okay, so there is a negative feedback is there. So as negative feedback is there, so this V0 prime, we can write easily that the gain will be this minus R1 upon Ri. Okay, so V0 prime, easily we can write that minus R1 upon Ri times Vi. So this thing you will get easily if you take KCL at this node. Okay, because 0 minus Vi upon Ri plus 0 minus V0 prime upon R1 will be equals to 0. From that also you will get this result. Okay, I hope it is clear, right? So you see, I am using simply inverting concept, then only we are getting these things, or you can use node analysis. Okay, fine. So this is V0 prime. Now once V0 prime is obtained, then we can find out V0. What we'll do? We'll apply KCL at node A. We'll consider this is node A. Their node potential is V0 prime. So if you apply KCL at this node, then what you will get? What the equation? So V0 prime minus 0 upon R1, because V0 prime, this is 0, virtually grounded. So V0 prime minus 0 upon R1, this current, and this current is V0 prime minus 0 upon R2, and this current is V0 prime minus V0 upon R3. That is equals to 0. So V0 up by R3, we can write that equals to V0 prime times 1 upon R1 plus 1 upon R2 plus 1 upon R3. Now we can replace V0 prime simply, and then V0 upon Vi we can do. So V0 upon Vi is simply write that this R3 I can multiply to right side, and so it is minus R1 upon Ri. It is there, okay? And then we can rearrange this 1 upon R1 and 1 upon R2, this addition I can take first, and then we will have 1 upon R3. So now if I simplify it, you will get the same result. This is R3 upon Ri, because R1 is cancelled out, then it is 1 plus R1 upon R2, and last term is R1 upon Ri again, okay? It is same result. So you see, just we have used only one node analysis. In the method 2, we have got this answer. So I'll prefer not to use any equation. Without an equation also we can solve this one. Okay, that also you can try. So, right, now I can give you, this is a homework problem, the problem I wanted to solve. Here only the equation values are given, so you can find out V0, and remember that this is load 8 kilo ohm. It will not affect your V0, it is independent of 8 kilo ohm. Okay, so voltages are given, so I think you can find out this V0, and post your answer in the comment section. If you have understood this method, I hope you will be able to find out this V0, and post your answer in the comment section. I'll surely reply. If you enjoyed this video, then please subscribe my channel. And to subscribe my channel, you should click here, and after subscription, you should also press the bell button. And this is a free channel, right? And thanks for watching. I hope you are going to subscribe this channel if you have not subscribed yet. And in this channel, I'll be adding more number of videos, lectures and tutorials. So keep watching. Thank you.